What's going on, everybody? Got another video here for you. Today we are doing the fundamental theorem for line integrals. Alright, so let's go ahead and get started. So we have a theorem here. It says let C be a smooth curve given by the vector function r of t, where t is between a and b. Let f be a differentiable function of 2 or 3 variables whose gradient vector is continuous on C. Then the integral over the curve C, the gradient of f dot dr, is equal to f of rb minus f of ra. And it says, note, we can evaluate the line integral of a conservative vector field, the gradient vector field of the potential function f, simply by knowing the value of f at the endpoints of C. We're going to read through the definitions, theorems and stuff, and then I'm going to explain what all it means. All right, so, and here's just a picture showing how that should be a minus right there. I don't know why I put an equal. But, you know, here's a curve here. We're going from A to B, and we can evaluate this by just evaluating f at the endpoints. And then here's one for 3 space. Okay. All right. So let's work an example, and then we've got some more stuff we got to read through, and then I'm going to explain it in simpler terms about what we're doing, what's going on. But let's just work through this example here real quick. This is a simple one. It says find the work done by the gravitational field F is equal to negative little m times big M times g over the magnitude of x cubed times vector x, and moving a particle with mass m from the point 3412 to the point 220 along a piecewise smooth curve C. All right. So we showed in an earlier video, it was the video on line integrals. Okay. We did an example, and we know that this function here is conservative. That's important here. The vector field has to be conservative in order to be able to use this. Okay, has to be conservative. Well, we know it's conservative because in the video entitled line integrals, we found a potential function, and you take the gradient of that potential function and you ended up with this. Okay, so later on, well, in this section we're going to learn how to show that f is conservative. We're going to learn how to show that it's conservative in 2-dimension, and in 3-dimension we're actually going to see later on how we can show that those are conservative. We're going to show that later on in a couple of sections or in a couple of videos. But we know that this is conservative, so don't worry about that right now. And so that means, let me change colors. So we know it's conservative, so that means f is equal to the gradient of some function f. And we know that f of x, y, z is equal to little m times big M times g over the square root of x squared plus y squared plus z squared. Okay, and we could find the gradient of this, and if we find the gradient of this function here, we would end up with this. Remember, it's the partial with respect to x, partial with respect to y, partial with respect to z. Okay? And like I said, go back and watch that video on line integrals, and it goes over how it goes over this. Okay? I'm not going to do it in this video, or it might be a little bit, be pretty long. But since we know that this is conservative, this is the potential function. Okay? So we can show that the work, the integral over the curve C of f dot dr is equal to the integral C gradient of f dot dr. Okay, that is right here. All right, and we did this I think a video or two ago. We did this. All right, and so this, since this is conservative and this is our potential function, then we can just evaluate the potential function at the endpoints. So that would be f of 2, 2, 0 minus f of 3, 4, 12, which that is going to be little m big mg over 2 squared plus 2 squared plus 0 squared, and it's the square root of that, minus little m big M g over the square root of 3 squared plus 4 squared plus 12 squared, which is equal to, and when you do the calculation, you get little m big M g times 1 over 2 square root of 2 minus 1 over 13. And there's your answer. Okay, so that's basically all we're doing is if we can show that the vector field is conservative, then we can evaluate the line integral used by this. Okay, that's what this right here is saying. Okay, all right. And we're going to work some more examples. We're actually going to work some examples where it kind of, we learn how to work a problem, but the steps of the problem are different examples. So we'll basically work a problem where we evaluate the line integral, but we're doing it in different examples. Each example is a different part of the problem. And then at the end, we got 2 problems to work where we just completely work them out. Okay. So it says, if f is a continuous vector field with domain D, we say that the line integral is independent of path if the integral over C1 is equal to the integral over C2 for any 2 paths C1 and C2 in D that have the same initial and terminal points. We can say line integrals of conservative vector fields are independent of path. So let's just read it and I'll explain everything. It says a curve is called closed if its terminal point coincides with its initial point, that is, R of B is R of A. If the integral over C f dot dr is independent of path in D and C is any closed path in D, we can choose any 2 points A and B on C and regard C as being composed of the path C from A to B followed by the path C2 from B to A. And here you have it. Okay, there's a picture of it, and we've got the integral over C is equal to the integral over C1 plus the integral over C2, which is the integral of C1 minus the integral over minus C2. In other words, you're changing directions. Since C1 and minus C2 have the same initial and terminal points, Conversely, if it is true that the integral over c equals 0 whenever c is a closed path in D, then we demonstrate independence of path as follows. Take any two paths, C1 and C2, from A to B in D and define C to be the curve consisting of C1 followed by minus C2. Then, so we have this, 0 is equal to the integral over C is equal to the integral over C1 plus minus C2, which equals the integral C1 minus the integral over C2. And so this integral is equal to this one. We have proved the following theorem, which the integral over C is independent of path in D if and only if this integral is equal to 0 for every closed path C in D. And then we have, there's a lot of theorems and definitions, and like I said, I'm reading through them right now, then I'm going to go back and explain everything. So theorem, suppose F is a vector field that is continuous on an open connected region D. If the integral over C is independent of path in D, then F is a conservative vector field on D. That is, there exists a function f such that the gradient of f is equal to f. Suppose it is known that f equals pi plus qj is conservative, where p and q have continuous first-order partial derivatives, then there is a function f such that f is equal to the gradient of f. That is, p is the partial of f with respect to x, and q is the partial of f with respect to y. Okay, that's where we were talking about potential functions and all that. Therefore, by Clairaut's theorem, the partial of p with respect to y is equal to this, which is equal to this, which is equal to the partial of q with respect to x. Okay, it's the second partial of f with respect to x and then y. And it doesn't matter what order you do it in. Okay, and I'm gonna explain all this when we go through the examples and stuff. So this right here, we have a theorem if f of xy is equal to p of xyi plus q of xyj is a conservative vector field where p and q have continuous first-order partial derivatives on a domain D. Then, throughout D, we have the partial of p with respect to y is equal to the partial of q with respect to x. So if it's conservative, that means we've got to have this. Okay? And here is a simple curve that's not closed, a simple curve that's closed. This is not a simple curve. See how it crosses here? And this is not a simple curve. This is not simple and it's not closed. This is not simple, but it's closed. And then we have a simply connected region and regions that are not simply connected. See how these two have holes in them and this one's split. Okay? And we're fixing to get to the examples. So we have a theorem, let f equal pi plus qj be a vector field on an open simply connected region D. Suppose that p and q have continuous first-order partial derivatives, and the partial of p with respect to y is equal to the partial of q with respect to x throughout D. Then f is conservative. All right. So basically, all that I just read, we're evaluating the line integrals of a conservative vector field. Okay? All right. So, to show that it's conservative, we show that the partial of p with respect to y is equal to the partial of q with respect to x. If we show that, that means it's conservative. And when it's independent of path, that means that, let's say you have, 2 points here, and this is your curve. Well, you can get from this point to this point by a straight line. You could come around here like this to get to the point, okay? Or, you could go, well, it's not erasing. There we go. I mean, you could come up here like this. Like that. Okay? It doesn't matter what the path is. If it's independent path, if that vector field's conservative, it doesn't matter the path that it takes to get from one point to the other. We can just evaluate it by evaluating our potential function at this point minus and evaluate it at this point, and that will give us the answer. Okay? So that's that's basically what all that's saying. Okay? All right. So let's look at some examples. So these first several examples that we work, they're just the steps of evaluating these integrals. Okay? So the first thing we would need to do when we're evaluating these is we want to determine if the vector field is conservative or not. Okay? All right. So let's look at part at A. So we've got P of xy is equal to x minus y, and Q of xy is equal to x minus 2. And so we take the partial of P with respect to y, that's equal to -1. Then we take the partial of Q with respect to x, that's equal to 1. So you see how the partial of P with respect to y does not equal the partial of Q with respect to x. So that means this is not conservative. Okay? It's not conservative. So all we're doing right now is we're just determining, is the vector field conservative or not. So here we've got P of xy. Remember, P of xy is what's in front of I. Q of xy is what's in front of j. And so this is 3 plus 2xy. And Q of xy is equal to x squared minus 3y squared. So if we take the partial of P with respect to y, we get 2x. And if we take the partial of Q with respect to x, this is equal to 2x. Now remember, when you take the partial with respect to y here, I mean, of course, the derivative of 3 is 0. And then remember, the x is a constant. So this is just 2x. And when we take the partial with respect to Q, the partial of Q with respect to x, well, remember the y term is a constant, so that's derivative, that's just 0, and then that's 2x. So we have the partial of P with respect to y is equal to the partial of Q with respect to x. So this is conservative. Okay? All right. So we determined if the vector field is conservative or not. All right? That was that example. All right. Let's look at this one. It says if f of xy is equal to this, find a function f such that f is equal to the gradient of f. All right, so the first thing, we know that f is conservative. We showed that. This was part B right here. Okay, we showed that it's conservative. So since it's conservative, there exists a function f with the gradient of f is equal to f. Okay, so remember f, this f right here, that's your potential function. All right, that's what we're wanting to find. We're wanting to find the potential function. So if you remember, all right, so remember we have the gradient of f equals f. So if you remember, when we took the gradient of f, okay, the gradient of our potential function, do you remember that when you do the gradient, this is the partial of f with respect to x, this is the partial of f with respect to y. So we have the partial of f with respect to x is equal to 3 plus 2xy, and we have the partial of f with respect to y is equal to x squared minus 3y squared. Remember how you took the gradient. It's the partial of f with respect to x times vector I plus the partial of f with respect to y times vector j. All right. So when you're going to find the potential function, this is the procedure that we use. Okay. Use this procedure here. So what we want to do is we're going to take this function here and we're going to integrate it. So we're going to find f of xy is equal to the integral of 3 plus 2xy. Okay. And we're going to integrate that with respect to x. Okay. And so this is equal to 3x plus x squared y, right? X squared y. Now, remember when you learned how to do integrals, remember how your teacher hammered it into you? Plus some constant c. So plus c. Okay? But hang on just a second. All right. Hang on a second here. So, yes, c is a constant. But remember, this right here, our variable is x. Okay? Our variable is x. So if we look at this constant here, in this function, okay, remember, x is considered our variable. We integrated with respect to x. Would you agree that something like y squared, if we just had a y squared there, that would be a constant, right? Y would be considered a constant. Or if we had, something like this, y squared over the square root of y plus 1, that would be a constant also, right? So a constant would also be some function in terms of y. So instead of saying plus c, we're going to say plus g of y. Okay, yeah, I mean, it could be just a number or it could be some function in terms of y. So we call this, we write our constant as g of y. Okay, so we have f of xy is equal to 3x plus x squared y plus g of y. All right. Now, we need to figure out see if we can figure out what g of y is. Okay. Well, if we take the partial of this with respect to y, we get what? X squared plus g prime of y, right? We're taking the derivative with respect to y. So y is our variable. Okay. Well, let's look at this. Wouldn't this mean that x squared plus g prime of y is equal to, so notice this right here. This is our f prime, our f of xy, our partial of f with respect to y. And notice up here we have partial of f with respect to y. So if we set these two equal to each other, that's equal to x squared minus 3y squared. And then we solve for g prime. Well, the x squareds cancel out, and I'm left with g prime of y is equal to negative 3y squared. Okay? So that tells me, and see what I'm needing to find is I need to know what g of y is. Well, g of y would be what? The integral of negative 3y squared dy, right? Integrate with respect to y. And this would give me negative y cubed plus some constant k. Now, in this one, we're going to use k as a constant because our function here is only in one variable. See, for our constant here, we use g of y because our function is in two variables. And in this case, we're integrating with respect to x, so y is considered the constant. So we wrote our constant as g of y. But here we only have one variable, y, so we just write plus our constant k. Okay, so now I have f of xy is equal to, well, what is f of xy? F of xy is this thing right here. So f of xy is 3x plus x squared y plus g of y. Well, what's g of y? It's this right here, minus y cubed plus k. And there's your answer. And this is your potential function. And this is the function that when they ask you to evaluate the integral, and it's a conservative vector field, okay? So think about this. We show that it's a conservative vector field, and then we find the potential function, and then you would evaluate the potential function at those endpoints. You would subtract them. And then that would give us, that was how we would evaluate that line integral. So basically what this is another way to evaluate line integrals if the vector field is conservative. Okay? So you might be asking, well, what if it's not conservative? Well, that goes to the last video, the section before this. If it's non-conservative, then remember what we had to do there. We had to reparameterize everything. We would rewrite it in terms of t. Remember that? Okay. So that's how you would have to work it. So this is just an easier way to work it. So if you have a vector field, if you can show that it's conservative, you find the potential function, and then you just use this, where is it? Well, it's on up here. You use this right here. And we're going to work some examples, 2 examples completely out. Okay. We're just learning right now, which is, it's going to be the more difficult part of the problem, is finding the potential function. That's the main part of the problem. I mean, plugging in numbers and evaluating, that's easy. Okay. All right, so let's look at this. Okay, so here's one where we're going to work it completely out. I mean, I think it's the same problem that we just did. Yeah, it's the same problem, but this time they give us a curve. Okay, so it says evaluate the line integral where f of xy is equal to 3 plus 2xyi plus x squared minus 3y squared j, and c is the curve given by this. Okay. All right. So we know this is a conservative vector field. We already showed that, right? We already showed that it's a conservative vector field. We've got p of xy is equal to 3 plus 2xy, and q of xy is equal to x squared minus 3y squared. And so if we do the partial of p with respect to y, that's going to give us 2x, and the partial of q with respect to x, that's going to give us 2x. So that shows that it's a conservative vector field. We already showed that earlier in an example. Okay, so we know it's a conservative vector field. So let's go ahead and find the potential function. Okay, so if you remember this right here, we just found the potential function. Okay, that's what we did in this example. So basically, to work this problem here, you would need to do what we did here, show that it's conservative, and then you would do this, find the potential function. Okay, and then we're ready to evaluate it. Now, like I said, later on we're going to do 2 examples where we're going to do it like this example and the previous 2. It's all going to be put together in one problem. All right, so we know, so we got our potential function is equal to 3 plus, now let's see, what's my potential function? Where is it? There it is. It's 3x plus x squared y minus y cubed plus k. All right, so to get to this point, we'd have to do what we did in the previous 2 examples. All right, so to evaluate this line integral over this curve here, where t is between 0 and pi. Okay, so we've got to figure out what our points are, right? So I've got r of 0, right? I'm going from 0 to pi. So r of 0 is e to the 0 times sine 0 I plus e to the 0 cosine 0 j, which that is equal to 0, 1, right? And r of 1 is equal to e to the 1 times sine, no, I'm sorry, not 1, of pi is e to the pi times sine pi I plus e to the pi cosine pi j, which this is 0, and this is what? Negative e to the pi, because cosine pi is negative 1. All right, and so we're going from 0, 1 to 0, negative e to the pi. So we have the integral over c dot dr is equal to the integral c gradient of f dot dr, which that is equal to, now remember the very first thing we learned, that's f of 0, negative e to the pi minus f of 0, 1. That's what it is. Okay, all that we went over, all that stuff written in blue that I read through, that's basically what it's saying. You can show it's conservative, find the potential function, and then you can just evaluate the potential function and find the difference. And so you're just plugging this in for x, this in for y, into your potential function here. So that's going to be 3 times 0 plus 0 squared times, let's see, times negative e to the pi minus negative e to the pi cubed. Okay, that's taking this and plugging it in here. Now, do we need to worry about writing the k in there? No, you don't have to worry about writing the k in there, because if you did, you'll have say you have a plus k, and then you're going to plug this in, you're going to subtract, you would have a plus k here. Those k's are going to cancel out. so we don't need to worry about putting that in there. So then we've got minus, now we plug the 0 in, so that's 3 times 0 plus 0 squared times 1 squared minus 1 cubed. All right, and when you evaluate all of this, you do your arithmetic, you get e raised to the 3 pi plus 1, and there's your answer. Okay, so there it is. But like I said, stick around. We're gonna do 2 more examples where we find all this stuff. But before we do that, we're gonna do this one. So what we learned how to do, or what the main thing that we did, is we found the potential function for 2 dimensions. We had a function in in 2 variables. We had a function in terms of x and y. See, our vector field was a ij. Well, what if we have a ijk? We have 3 variables, x, y, and z. Let's find the potential function. So this one's going to be a little more involved. Okay, so let's go ahead and do that. So this is a conservative vector field. Okay, so when we have an ijk, we can show that it's a conservative vector field once you find the, so for instance, this one right here, we've got our potential function. We could find the gradient of this. And that would give us this. Okay, that's a way you could show that it's conservative. But like I said, later on in a couple of sections, we're gonna learn how to, if we have, and then when we just have an ij, we can show it's conservative by showing the partial of p with respect to y is equal to the partial of q with respect to x. But when we have an ijk and we have the 3 variables here, once you find that potential function, you can find the gradient and show that the gradient of the potential function is equal to this, and that would show that it's conservative. But later on, we'll learn how to determine that this is conservative before doing all that. Okay, so remember, this is a conservative vector field. So we have f of x, y, z, the partial of f with respect to x is equal to the part in front of I, which is y squared, and then the partial with respect to y is equal to this part in front of j. Remember, I explained all this earlier. 2xy plus e to the 3z, and the partial of z is equal to 3y e to the 3z. All right, so let's find the potential function. We're going to do it just like we did the last one, except we do have 3 variables here. Okay, so I'm going to integrate. I've got f of x, y, z, okay, f of x, y, z is equal to the integral y squared dx. Okay, we're using this one. We're going to integrate with respect to x, okay, and so this is going to give me x, y squared plus some constant c. Okay, so if you remember in the last example, what did we use as our constant? We used g of y, right? G of y. Well, how could we write a constant here? Remember, x is our variable. Okay, x is our variable. So our constant would be g of what? G of y z. because y and z are considered constants. We're integrating with respect to x. So if we have some function in terms of y, that would be a constant. That would be considered a constant. Or if this was some function in terms of z, that would be a constant. Or if this was some function in terms of y and z, that would be a constant. I don't know if I said a function earlier. If I did, I meant constant. Okay, that would be a constant also. Okay, so I've got f of x, y, z is equal to xy squared plus g of y, z. All right. So now what I want to do is I want to take the partial of this with respect to y. So the partial with respect to y is equal to 2xy plus, now how would we write this? Would I just put a prime there? No, because this is a function and this is two variables. So I'm taking the partial of g with respect to y. Okay? All right. Now, notice how I have the partial of f with respect to y, and I have this partial of f with respect to y. So I can set those equal to each other. So that's going to give me 2xy plus the partial of g with respect to y is equal to 2xy plus e to the 3z, which the 2xy's cancel, so I get the partial of g with respect to y is equal to e to the 3z. All right, so let's look at this. So what do I need to find? All right, see, here's my potential function that I'm building up. I need to know what g of yz is. Well, I've got this. So g of yz would be what? The integral of e to the 3z, right? E to the 3z with respect to y. Okay, I'm going to integrate this thing with respect to y. And so that would give me what? Y e to the 3z plus some constant. Now, remember, I'm in terms of y and z here, in terms of y and z. So my constant would be what? It could be just a number, or it could be some function in terms of z. So we'll just write this plus h of z. Okay. So now I have f of x, y, z is equal to, well, there's f of x, y, z. Just keep writing all this out, because if you don't write down, like take this and put it in the place of this, and keep writing it down, it's easy to lose track. So this is xy squared plus g of yz, which is this thing, plus y e to the 3z plus h of z. Okay. Now, what we're doing now is we actually need to figure out what h of z is, right? We need to figure out what that is. So we're going to take the partial of f with respect to z. Okay. And so this is 0. This would be what? 3y e to the 3z plus h prime of z. Okay. Now, look at this. Let's see. We'll use this color. There's f of partial of f with respect to z. And here is the partial of f with respect to z. So we're going to take this and set it equal to this. See? Take this one and set it equal to this one. So that's going to give me 3y e to the 3z plus h prime of z is equal to 3y e to the 3z. Okay, so this first part is this, and then this second part here is this up here. And so this tells me that h prime of z is equal to what? 0. Well, the derivative of what is 0? Remember, the antiderivative, we're going backwards, okay? What did I take the derivative of to get this function? Well, what do you take the derivative of to get 0? A constant. So this tells us that h of z is just equal to some constant k. Okay, so that tells me that f of x, y, z is equal to, okay, so now I'm looking at this. You see that? There's my potential function. See how I'm slowly building it up? So this is going to be x y squared plus y e to the 3z plus h of z, and we determine h of z is k, and there's your potential function. So like I said, that's going to be the most difficult part, is finding the potential function. I mean, it's not really difficult to show that they're conservative, and it's not difficult to evaluate the potential function at those two endpoints. This is the work right here, is finding that potential function. Okay, all right, so now let's look at some examples. Okay, this is where we're just working them all the way through. We're just evaluate the integral along the given curve C. Okay, that's what we want to find. Okay, so remember how we did it last time. Okay, remember what you did in the last video. You would reparameterize and put everything in terms of t and do all that stuff, do dot products. Okay, well, if our vector field is conservative, then we can just evaluate the endpoints and find the difference. It makes it a lot easier. Of course, we got to find the potential function, but I think that's easier than what we did in the last section. And remember, it has to be a conservative vector field. If it's not conservative, then you've got to go to what we did in the previous video or the previous section. All right, so let's look at this. So basically what we're doing in this problem is what we just did in all those examples. Okay, all those examples that we worked, they're all getting put together to work a problem, to evaluate this integral. All right, so we've got p of xy is equal to x squared y cubed. Q of xy is equal to x cubed y squared. So the partial of p with respect to y is equal to 3x squared y squared, and the partial of q with respect to x is equal to 3x squared y squared. And so we showed that these partials are the same, so that means this is conservative. Okay, so now we can find, so that tells us that f of xy is equal to the gradient of f. Okay, so we need to find our potential function. Okay, so let's find our potential function. So we have the partial of f with respect to x is equal to what? That's equal to x squared y cubed, and the partial of f with respect to y is equal to x cubed y squared. Okay, remember, this is partial f with respect to x, this is partial f with respect to y. Okay, so now we have f of xy this is our potential function, is equal to the integral x squared y cubed with respect to x. Okay, so this is equal to what? 1/3 x cubed y cubed plus some constant. What's our constant? We're in terms of x and y. Y is considered a constant, so that's plus g of y. Okay, and then what am I going to do? I'm going to take the partial of this with respect to y, and that's going to give me x squared y cubed plus g prime of y. Okay, I hope all this makes sense. Okay, now what do I do now? I take this and I can set it equal to this. Those are both the partial of f with respect to y. So I've got x squared y cubed plus g prime of y is equal to x cubed y squared. So I get g prime of y is equal to 0. So this tells me that g of y is equal to some constant k. So now I have my potential function f of xy. See this right here, this is my, well, right here. Oh, well, where did I write that? Well, it's right here. F of xy is this. Okay, so that's going to be 1/3 x cubed y cubed plus g of y, which g of y is some constant k. All right. So this is my potential function right here. That's my potential function. So now all I do is evaluate it at the endpoints. Okay, so what are my endpoints? Well, this right here, along this curve from t equals 0 to t equals 1. So what I'm going to do is I'm going to take this and write it down below again, so we can see it. All right, so I wrote down r again just so we could see it. So I need to go from when t is 0 to when t is 1, from that point to that point. So when t is 0, so I've got r of 0 is equal to 0 cubed minus 2 times 0, 0 cubed plus 2 times 0, which is equal to 0, 0. And then r of 1 is equal to 1 cubed minus 2 times 1, and then 1 cubed plus 2 times, oh, wait a minute. Yeah, 2 times 1. And that is going to be, what is that? -1, 3. So I'm going from 0, 0 to -1, 3. So we have the integral over c of f dot dr is equal to the integral c gradient of f dot dr, which is equal to f of -1, 3 minus f of 0, 0. That's how we integrate it. Okay, and so this is going to be 1/3 times -1 cubed times 3 cubed minus, and we don't need to put the k in there, they would cancel out. That's 1/3 times 0 cubed times 0 cubed, and this is equal to -9. And that's evaluating this vector field over that curve. That's what we found. Okay, and I ended up finishing all that in green. I usually write it in with a white marker, but oh well. All right. So basically what they're doing is they're saying evaluate this line integral over this for this vector field over this curve from this point to this point. See, from this point to this point. And we had to figure out what the point was. We had to take the 0 and the 1 and plug it in here and figure out what get our x, y. All right. So that's all you're doing. Okay, so let's look at this one. It says evaluate this along the curve C. F of x, y, z is equal to this. There's our vector field. And C is the line segment from this point to this point. So what they're doing here is they're not saying, okay, it's going over this curve here where T is between those 2 points. And then we find our points there. They're going ahead and giving us that in this problem, which that's nice. So that just saves us a little bit of work. And this is x, y, z. We have an I, j, k. So we got to find our potential function. So that's going to be like what we did in that we worked an example like that where we found the potential function. All right. So we're going to go and assume this is a conservative vector field. Okay. Like I said in a couple sections, we'll learn how to show that's a conservative vector field. Basically what it is you'll learn how to find the curl of f. And if the curl of f is equal to 0, it's conservative. But we don't know how to do that yet. Okay. But that's in a couple of sections. But we can verify it. Once we find the potential function, we can take the gradient of that potential function, and if we get this, then that tells us it's a conservative vector field. All right, so let's go ahead and get started. So we've got f of x, y, the partial of f of x, y with respect to x. That's equal to 2xy. That's this part. And then the partial of f of x, y with respect to y, that's equal to this part, x squared plus 2yz. And then the partial f of x, y, z. We're in 3 variables. That is equal to y squared. So there's your partial of f of x, y, z with respect to x, with respect to y, and with respect to z. So let's find our potential function. Okay. All right. So we've got f of x, y, z is equal to, so what I'm going to do is I'm going to integrate this, the 2xy, with respect to x. Okay, integrate it with respect to x. And so this is just going to be what? X squared y, right? X squared. Yeah, x squared y plus our constant. Well, what is our constant? Well, remember, our variable is x. Everything else is a constant. So we've got a x, y, z. So this is going to be plus our constant, g of y, z. So if we have a function in terms of y, we have a function in terms of z, or if we have a function in terms of y and z, those are all considered constants. Because our variable is x. We integrated with respect to x. Okay? All right. So now let's take the partial of f with respect to y. So that's going to be what? X squared plus the partial of g with respect to y. Okay? And so now let's take this and set it equal to this. See, partial f with respect to y, partial f with respect to y. So that's going to give us x squared plus the partial of g with respect to y is equal to x squared plus 2yz. And so this tells me that the partial of g with respect to y is equal to 2yz. Okay, see, the x squareds cancel out. So now I have f of x, y, z, my potential function. F of x, y, z is this, right? So that's equal to x squared. No, wait a minute. Oh, I'm sorry. I jumped ahead of myself. My bad. Not that. We've got this is our potential function. I looked at the wrong thing. I don't know what I was thinking. My brain went dead for a minute. All right. So here's my f of x, y, z equals this. I need g of y, z. So I know g of y, z is equal to the integral of 2yz, and I'm integrating that with respect to y. Okay? And so this is equal to y squared z plus our constant. Now we're in terms of y and z, so my constant, I can write that as h of z. Okay? So now we have f of x, y, z is equal to, that's this thing. That's f of x, y, z. That's equal to x squared y plus this, y squared z plus h of z. Okay, y squared z plus h of z. And that is, let's see, where is it? That's plugging this into here. Okay. All right. So now I need to figure out what h of z is. So I'm going to take the partial of this with respect to z. So that's going to give me y squared plus h prime of z. Okay, that's the partial f with respect to z. So now I'm going to take this and set it equal to this. Isn't this the partial with respect to z? Is y squared. So I've got y squared plus h prime of z is equal to y squared, which this tells me h prime of z is equal to 0. And we did something like similar to this earlier. So that tells me that h of z is just k. Because when you take the derivative of a constant, that's how you get 0. Okay, so now I have f of x, y, z is equal to, I found h of z, which is k. So that's x squared y plus y squared z plus some constant k. All right, so this is my potential function. There's my potential function. And what did they want us to do? They wanted us to go from this point to this point. So let's just write the 2 points down here. We're going from the point 2, -3, 1 to -5, 1, 2. Okay, so we've got the integral over our curve C, f dot dr is equal to the integral over C gradient of f dot dr is equal to f of -5, 1, 2 minus f of 2, -2, -3, 1. And so this is going to be -5 squared times 1 plus 1 squared times 2. And we don't need to worry about putting the k in there. They're going to cancel out. That's minus, let's see, plug that 2 in there. That's 2 squared times -3 plus -3 squared times 1. And that is equal to 30. There's your answer. Okay, so this is a method for evaluating the line integral where we have a special case. The vector field is conservative. So if the vector field's conservative, that's what it's telling us, that we can evaluate the integral using this. Doesn't matter the path. It's independent of path. It doesn't matter how it gets from one point to the other if it's conservative. That's the key to this section. Okay? If it's conservative. If it's not conservative, then like the last section. But that's basically all you're doing here. You got to find the majority of the work, well, really pretty much all of the work, is finding the potential function, is finding this thing right here. That's what we have to do. But hopefully you can see now those first examples that we worked was just all of this. And now it's just putting it into one problem and evaluating it. Okay, they were in those examples, they're just kind of walking you through it step by step. Okay, show that it's conservative. Find the potential function. And that's basically all you're doing. Okay. All right, so I hope you enjoyed that video. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.